right, in this video, we're going to graph exponential functions with and without technology. Mainly, we're going to avoid technology because in what we're doing, it really just gets in the way. And the fact that we're going to use the conceptual method to graph logarithms and how they are inverses of exponentials in the first place, technology really is going to get in the way. So try to make sure you do this the way I'm doing it and not necessarily lean on your calculator too much because it'll only get in the way down the road. So with that said, number one, graphing 3 to the x. To graph the picture of y equals 3 to the x, you need a bunch of points to illustrate that picture. So I picked some x's to plug in. Mental math we can do. 3 to the 0 would give us 1. 3 to the 2 would give us, so 3 to the 1 would give us 3. 3 to the 2 would give us 9. And then 3 cubed, 27. 3 to the 4th, 81. Mental math going backwards, 3 to the negative 1 would be flip that 3 to the negative 1. Exponent negative takes 3 to the bottom, so 1 over 3 to the positive 1, meaning you'd get the fraction 1/3. And get the right color going here, 1/3. 3 to the negative 2 then would flip that fraction, or would take the 3 to the denominator and square it, so 1 over 9. And I think you kind of see the pattern developing here, 1 over 27, 1 over 81. And to graph those, we'd need to count by something different on the y-axis, so we're going to count by 3 on that problem. Let's go ahead and do number 2, mental math, as well, while we're here thinking along the lines of mental math. 1/4 to the 0, 1/4 to the 1, 1/4 to the 2. Okay, so 1/4 to the 0. Anything to the 0 power is 1. 1/4 to the 1 is a 4th. 1/4 squared would be square the 1, square the 4, so 1 over 16. 1/4 cubed, 1 over 64. And then 1/4 to the 4th would be 1 over 4 times 4 times 4 times 4, 256. So a very, very small decimal. When you start going the other direction, 1/4 to the negative 1, it flips the fraction to 4 over 1 to the positive exponent 1, which is really 4 to the 1, or just 4. And then when you put the negative 2 in for the exponent, it flips the fraction and squares it, so 16. Negative 3 in for the exponent, flips the fraction and cubes it, so 64, and then 256. Again, I think you see the pattern in numbers without involving the technology, which would have given you decimals in the place of fractions. So now, graphing, we're going to count by 3 in the first problem and count by 4 in the second, because our points on the y-axis kind of match up to counting by 3s and 4s. So I'm going to do this kind of quick, but counting by 1s and counting on the x-axis and 3s on the y-axis is kind of difficult, so take your time if you're recreating this yourself. But 0, 1, probably 1, 3. That'd be the first point I'd graph. Right 1, up 3 is literally up 1. 2, 9, right 2, up 3, 6, 9. 3, 27, right 3 and up 3, 6, 9, 12, 15, 18, 21, 24, 27, and that's going to be the last one that fits. So now going backwards and graphing 0, 1 would be kind of up a third if you're counting by 3s. Graphing negative 1, 1/3, that'd be left 1 and up a little. Negative 2, a 9th, left 2, up a little. In fact, your pencil lead is probably thicker than a 9th. So at this point, our decimal points that we're graphing are just a little bit above the x-axis. We can't really distinguish any better than that. So negative 3, 1 over 27, so left 3, up a little, left 4, up a little, and so forth and so forth. So we connect these dots to illustrate all the decimal points that are in between the values that we plugged in, because we could have plugged in decimals, but we would have needed technology to find them. And then a couple more questions about the picture. Exponential. Is that growth or decay? You read a graph like you read a book. So from left to right, that's going up. It's growth. And anytime your base is bigger than 1, you're going to have exponential growth. So when that 3 is bigger than 1, you're going to have growth. Domain and range. Domain. What can you plug in for x? Well, we plugged in negative 4 to 4, but we could have plugged in anything. There's nothing that restricts what you can plug in your exponent, 3 to the blank. So all real numbers. The range. Well, focus in on these decimals. 1/3, 1/9, 1/27. We'll notice that those decimals keep getting smaller and smaller and smaller, and they will get closer and closer and closer to y equals 0, but they'll never get there because the fraction always has a 1 in the top, so your range is greater than 0. Similarly, we'll see some things in number 2 here that we saw in number 1, except our growth will actually be decay here, but let's go ahead and graph the easy points. Let's see, -1/4 is probably the easiest to graph when you're counting by 4. Left 1, up 4, so left 1, up 1 when you're counting by 4s on the y-axis. Left 2 for -2, 16. Left 2, up 4, 8, 12, 16. -3, 64. It's not going to fit on this picture, but we'll go ahead and kind of graph this as though we're going towards that point. Then we'll go and graph 0, 1. That would be up about 1/4 when you're counting by 4s. 1, 1/4, right 1, up a little. 2, 1/16, right 2, up a 16th, up a little. 3, 1/64, right 3 and up a little, and you see the point. We're seeing, or getting the point here. We're seeing those same decimals getting closer and closer to 0, but they'll never actually get there. Therefore, your range, once again, will be greater than 0. This is decay because we're reading a graph like we read a book from left to right, and from left to right, this graph's going down. And domain, once again, we could have plugged in anything, so all real numbers. All right, now that part's pretty easy and pretty straightforward. The conceptually difficult, or at least challenging part, is we're going to start messing with the input and the output of exponentials, and eventually the input and output of logarithms to see how that affects the original picture. Does it move it left, right, up, down? We did some of this with quadratics, and we'll see some similar patterns that we saw with quadratics. And to start that discussion, we need to look at 481, in other words, 3 to the 4th, and kind of think about graphing 3 to the x minus 1 in the aspect of how would I take a missing number, the box that I've got illustrated here. How would I take a missing number and subtract 1 and then it turn into 4? Well, you'd want to put a 5 in that box. So if you put 5 into this new function, essentially you get 3 to the 4th. So if you put a 5 in for x, you essentially get 3 to the 4th. You get that 81 that you had previously for 3 to the 4th. All right, so let's think like that again on another one. Let's see if we can do that one more time at least. What would you put in for that box, which is the x of our function we're graphing, so that that turns into 3 cubed? Well, let's see. Blank minus 1 turns into cube. We'd want to put a 4 in there. So we'd want to put a 4 in for the x. Put a 4 in for x. Change these to blue. 4 in for x to essentially get 3 to the 4 minus 1 to get 3 cubed, which would give us an output of 27. And you might start to notice the pattern here. 481 became 581. 327 became 427. Essentially what's happening here is the x values are 1 bigger. And if the x values are 1 bigger, that means the x values have moved to the right 1. Think about the point 481 versus 581. If you graphed 481, it would be right 4, up 81. 581 is right 5, up 81. So it has moved to the right 1. So moral of the story, when you subtract 1 to the input, you've changed x. You've moved it right 1. So we can go ahead and move every x value right 1. So 3, 2, 1, 0, -2. I'm sorry, -1. Don't know where that came from. -1, -2, -3. And you will essentially get the outputs that you had for 1x less than that. So in other words, when you put that 3 in, 3 to the 3 minus 1, you get 3 squared. You get 9. And then 3, and then 1, and we're just copying the rest of those y values since we've noticed the pattern. And 1/81. All right. We aren't going to actually graph this one, saving time in the video. I'm just going to illustrate that those decimals right there got closer and closer to 0 again. So your range is still going to be greater than 0. Your domain is still anything you want to put in, And since we shifted the points right 1, it's kind of like we've put anything you want to put into this function plus 1. But the definition or the very essence of infinity, all real numbers, if you add 1 to everything, you still got everything. So the domain is still all real numbers, and this one is again going to be growth. But saving time on the video. The next one, 1/4 is the same as the decimal 0.25. So we're going to compare number 4 to number 2 that we graphed. They have the same base, so basically the question is what happens when you add 2 after the exponent? Well, it's going to change the output. Now to see that happen, let's start with plugging in. Let's keep this easy on ourselves. Let's put in a -4. So if you take 0.25 to the -4, according to the table above, 1/4 to the -4 gives you 256. So if that turns into 256, what happens when I add 2? I get 258, meaning input of -4 gave us an output of 256 plus 2 of 258. We'll do one more like that. If you take the input -3, so 0.25 to the -3, according to the table above, you get 64 for that. So 64. What happens when you add 2 to that? You get 66. So input -3 gave us 66. And I think from that you can already tell the pattern. Adding 2 in that spot where it's been added, it's highlighted in blue. Adding 2 after the exponent essentially adds 2 to your output, to your y values. So I'm just going to continue to add 2. So 18, from the 16 add 2, from the 4 add 2, from the 1 add 2, and then I'll use the decimals here. 2 plus 1/4, 2.25. 2 plus 1/16. I'm going to use my calculator here in the classroom because it's a lot quicker than the one on screen, but 2 plus 1/16 is the decimal 2.0625. 2 plus 1/64. 2 plus 1/64 is the decimal 2.015625. So about 2.016, around that, the 3 decimals. 2 plus the fraction 1/256 is about 2.0039, so about 2.004. When you put in the inputs, -2, -1, 0, 1, 2, 3, 4. Meaning, adding 2 to your output will not change your inputs. It's only going to change the output. It's going to add 2 to all of them. Now I'm going to graph this one because it does affect domain/range, one of the two. And graphing, I'll still count by 4s like I did in number 2. And the first one I'll graph is 0, 3. Counting by 4, that'd be about right there. -1, 6. That would be left 1, up 4, up 6. About right there. -2, 18. That'd be left 2 and up 4, 8, 12. 4, 8, 12, 16. And then 2 more, so 18. And 66 is not going to fit, so I'll go ahead and send that picture up to the point -366. Now, here's where it changes domain / really it changes range. Graphing 1, 2.25 would be right 1, up 2, 0.25. Graphing 2, 2.06, right 2, up 2.06. Right 3, up 2.01. Right 4, up 2.004. What's happening here is you're getting closer and closer. The decimals are getting closer and closer to 2. Not 0, but 2. So your y values are getting closer and closer to 2. They'll never get there, so your range has been changed. It's greater than 2 now. The +2 affected your range. The domain, you can still plug in anything you want, so all real numbers, and this is decay. You read a graph like you read a book. All right, this last part is only for calculus-bound students, just a quick little introduction to horizontal asymptote, because we're not going to do a whole lot with it here in Algebra 2. But there is a horizontal asymptote, y equals 2, a horizontal line at y equals 2. Try to draw one best I can here. Y equals 2. I need to move that one up just a little bit. Like that. There we go. It's probably as good as I can do here. That's y equals 2. That horizontal line, the graph of 1/4 x plus 2 gets closer and closer to that horizontal line, but it never actually gets there. And that's going to be significant when you get into higher level math such as calculus, and it's called the horizontal asymptote. There was a horizontal asymptote in both of the first two problems at y equals 0, also known as the x-axis, because it got closer and closer to y equals 0, that horizontal line, but never actually got there. So that's the shortest I can do, so around 15.5 minutes for target 3. If you watch this as a review, I would recommend watching target 5 next, because there's going to be a lot of similarity to this conceptual form of graphing.